Hi everyone. So this is not really a research talk. This is almost everything here is going to be things that you already know. So the main purpose of this talk is just to try to bring together some strands of machine learning, different areas. Try to, it's just a bunch of stories. Think of it that way. About regularization, right? So regularization is something that comes up all over the place in machine learning. And everywhere it comes up, people have a different reason for doing it, or a different rationalization, or a different origin story, if you will. So I just want to sort of, talk about some of these. This talk won't be very technical. It will have a little bit of audience participation, so we'll see how that goes. And yeah, so let's get started. So we like the best of things, right? Like we like the best estimator. If you want to estimate something, why would you settle for anything that's not the best, right? But clearly, best can mean different things to different people. So here's where the audience participation comes in. So here's the problem, right? A really simple problem. You have a normal distribution with some mean, theta, and the covariance matrix is this identity. So it's a multivariate normal distribution. And you have one sample trial. That's all you have. And you want to estimate the unknown mean, right? Seems like a simple problem. And the covariance matrix is known to be the identity. And what would you do? So there's no right answer, there's no wrong answer, but what would you do? Yes?
I would use my sample.
Right? Use a sample, so use
As the mean.
Y itself to be the mean, right? And Nico, you had the same idea. So that seems like a pretty straightforward solution. Does anyone have any other ideas? Like, it's not clear what else you would do, right? I'm cheating a little bit because I haven't defined what best means, right? So I'm asking you to solve an undefined problem, right? But, a pretty standard solution to what best means is to use the mean squared error, right? So the mean squared error is just the expected square distance between our estimate and the true value, right? And we could pick this estimator, which is this, estimate theta hat using y. And it turns out it's an unbiased estimator, so that's always good. But it has a mean squared error of d, where d is the dimension, the dimensionality of the space over here. So you might be happy with that. If you really want things to be unbiased, then you're probably happy with this. But we didn't say anything about unbiased, right? We said we wanted the best mean squared error. So are there other estimators that are better than this in terms of mean squared error? So here's another option. It's almost the same. So I'm basically estimating using y, but I'm multiplying it by a constant 1 minus alpha. So think of alpha as a small number. So for example, if I pick alpha equals 0.1, then I'm just multiplying estimate by 0.9. Instead of estimating y, estimate 0.9 times y. And what does this accomplish, right? So clearly this introduces a bias, right? Because instead of the expected value being theta, you're away from the expected value by minus alpha times theta. But it also reduces the variance. So you're introducing bias, but reducing the variance. The variance, instead of just being d, becomes 1 minus alpha squared. Right? And the mean squared error is, of course, the bias squared plus the variance. So this is the bias squared and this is the variance. And now you might wonder, can I find some alpha such that this mean squared error is actually smaller than d, right? And it turns out you can, but that will only be better for some values of theta, right? And we don't know what theta is. So it's going to be hard to do this to find an estimator that's always better than our standard estimator for all values of theta, right? So that really hasn't bought this much, unless we know something about what theta is. But here, there's this thing called the James-Stein estimator. This caused a sensation when it was published around 1950. People didn't believe that this was possible, but you could pick alpha to be this quantity, d minus 2 over the norm of y squared, right? And this is not a constant, because it depends on y. But that's fine. I mean, that doesn't stop us from using it, right? It doesn't depend on any information we don't have. We are still just using the dimensionality of the space, and we're using the sample that we have, right? And it turns out that when the dimensionality of the space is more than 2, this estimator is always better than that unbiased estimator in terms of mean squared error, right? Now this is weird, right? Like, why is this happening? Why is this? First of all, why is this weird d greater than 2 condition coming from? Right? So there's all of these questions. If you are interested in these questions, you have an entertaining evening ahead of you on the internet. I'm not going to try to answer all of these questions. But what these estimators, so it turns out that you can apply this kind of principle to many different statistical estimation problems. And you get these things called shrinkage estimators. And essentially what you're doing is you're taking what you would think of as your normal estimate and you're shrinking them a little bit, which increases bias but also reduces variance. And in some cases you can balance things out to get better estimators than the other ones. It turns out that the reason that the James-Stein estimator works in this situation is because if you think of the vector of the components of theta, right? If you wanted to estimate each of them individually, there's not much better you can do. Right? If you wanted to estimate the first component or second component, you would pick the first and second component and so on. But it turns out that if you're trying to estimate all of them at once, and that's what mean squared error gives you, right? Because mean squared error is like the squared error added together for all the components. You can actually do a better job of estimating all of them together by a procedure like this. It will be a worse estimator for any individual component, but it's better in terms of mean squared error. Right? So these kinds of strange situations pop up in statistics. And it turns out that this weird procedure has an interpretation as a weird, something called an empirical Bayes method, which is not Bayesian. I mean, Bayesian reasoning is all about choosing a prior, picking a model, and getting a posterior. Empirical Bayes methods are where your prior is not fixed, but you pick a prior based on the data you see. So it's not really a Bayes method, kind of looks like one. Yeah, I'm just a messenger. Yeah. Okay, so this was our first story, right? So you can kind of interpret this as some sort of regularization, because our whole procedure was you start with some estimate, which seems like a reasonable estimate, and you shrink it towards zero. And if you know a little bit about regularization, that's kind of what many regularization principles do, right? Like you optimize the function, and that results in you shrinking. So that's our first story, right? I also mentioned that this was some sort of weird Bayesian method. And the second story is probably also familiar to many of you. It turns out that if you really, want proper Bayesian methods, you can interpret them in some sense as a kind of regularization. So in Bayesian inference, you have some unknown parameter theta, and you have an observation y, and you assume there's an observation model, right? Sorry, this should be backwards. Obviously, the observation model is py given theta, right? So typo, fix that. So the observation model is saying if the unknown parameter was theta, then what would the probability distribution over y? And you have some prior distribution which is p of theta, right? This is something that non-Bayesians kind of get stuck up on, like where does this prior come from? But Bayes' law tells us that the posterior distribution of theta given y is py given theta, so this is this model, the observation model times theta, which is the prior over this. And one way to sort of do Bayesian inference is to do maximum a posteriori estimation, which is basically to find the theta that maximizes the likelihood under the posterior distribution, right? And it turns out obviously that is the same as maximizing the log of the likelihood. So you're maximizing the log of that Bayes law thing, and that turns into the log of py given theta plus the log of p theta minus the log of py. This doesn't matter in this maximization because it doesn't depend on theta. I'm just putting it anyway. And these two terms are familiar, right? If you know what regularization is, you have some term that depends on the data, and you have another term, data and the model, another term that depends on the other model. So this is sort of classical regularization, right? You have a loss function, which is it's minus because usually you write an optimization and then minimization, so you have a regularization, right? So this is fairly straightforward. This is one of the classical ways that something like regularization shows up when you're doing machine learning. And it's just the interpretation of the regularizer is just the negative of the log prior, right? So that's how you're putting extra information into that problem. And that usually shrinks the estimate, right? So it depends, like for many common kinds of priors, for example, if you pick the like a normal distribution as a prior, then the log of it is going to be something like Euclidean distance, and so that's the same as L2 regularization, square regularization, and so the next. So that was the second story. The third story comes not from Bayesian inference, but from the whole side of machine learning that's called path learning, and probably approximately correct. And the setup there is that you have n data points, x1 through xn, and you're assuming now that they're drawn independently from a distribution, from a data distribution. And you have some hypothesis class, right? So for example, if you're doing binary classification, the hypothesis class could be the set of all rules that separate the positive class from the negative class. So if you're doing linear separators, then the hypothesis class will be the set of all given separators, accessibility classes, or whatever, right? And then you have some loss function, and the loss function for a particular data point, it basically evaluates a hypothesis on that data point and gives you a loss, right? So, for example, for binary classification, you could have a 0-1 loss or whatever, right? And the thing that you really want to minimize is, or you want to produce a hypothesis that performs well on the next data point that will be drawn from the distribution, right? So you want to minimize this quantity, the loss of the hypothesis of f when x is drawn from t, right? So the next sample is drawn from the distribution. So that's the actual risk, right? The true risk, but we don't know that obviously. What we do know is empirical risk. So because we have n samples from the distribution, you can approximate this using the loss that you have suffered on the data points that you have, right? So I'm using L for the true risk and L hat n for the empirical risk based on n data points. And this quantity is just a number, but this quantity is a random variable because it depends on the data points that you sample, right? And as n becomes large, you can kind of imagine by the law of large numbers that this function becomes close to that function, but we actually want to bound that, right? So the problem is that minimizing this empirical risk function doesn't necessarily minimize the true risk function. So you want to minimize this, you could try to minimize this, but you have to be careful because they're not the same thing. Okay, so let me just make a little picture. So suppose the true hypothesis is S star, right? So there is some true hypothesis, and it may or may not be in our hypothesis class, right? That's whether we're considering the realizable or unrealizable case. And what we care about bounding is excess risk, right? So how much worse is the hypothesis that we pick compared to sort of the best or the true hypothesis, right? So that's this. So the expected true risk of the hypothesis that we pick minus the risk of the best hypothesis. And so I've just introduced, basically I've added and subtracted this quantity, and I've grouped these terms. And this term is called the approximation error. It's the difference between the loss that you would have on the true hypothesis and the best you can do in your hypothesis class, right? So this is not something you can really reduce without increasing the size of your hypothesis class, right? It tells you the best you could do. This is called the estimation error, and this is basically the difference between the risk of the hypothesis you picked versus the best hypothesis you could have picked, right? So this is called the estimation error. And you can imagine that if you know the true loss function, you can bring this down to 0. Or in other words, if you have many samples of the data, then maybe you could bring this down to 0. But the game is basically trying to bring this down, right? This is the common picture that you might have seen. So this circle here is the set of all hypotheses. This is the true hypothesis. In this case, I've drawn it as being outside of this set. And this is the actual best hypothesis in the class. This is what we should have picked, but this is what we end up picking because randomly the data that we get might not be representative of all the things that we want to know about. So this difference is called the estimation error, this is the approximation error, and in some sense both of them contribute towards good error, right? But we want to bring this down. Okay, so that's kind of what I said. So if you increase the size of this hypothesis class, then usually you are reducing this error because you are making more and more hypotheses representable. But at the same time, learning a more complex hypothesis class usually increases estimation error as well. So you might know this, for example, the class of polynomials with big degrees, bigger than the class of polynomials with small degrees. And it's much more noisy. You need many more samples to learn polynomials of ID from a certain amount of data. So usually having more samples gives you less estimation error, and so you can then use a bigger hypothesis class, and that will also reduce your approximation error. But another approach is complexity regularization. So implicitly, I've been saying here that the hypothesis that you pick should be the one that minimizes your loss on the data you've seen, and you want to hope that that's actually a good hypothesis, right? But instead, it turns out that you can minimize your loss on the data you've seen, plus this function, Cn, the complexity function, and this complexity function depends on n, right? So the more data you have, maybe you pick different complexity functions, right? And it turns out that if you know something about the problem, you can pick Cn, and that will actually give you an upper bound on this excess risk that we care about. And the condition that you want on Cn is something like this. You want Cn to be like with high probability an upper bound or the difference between L hat and L. right? So it's basically, if you have some way of measuring how different the empirical risk can be from the true risk, and you can upper bound that by C, and you say that the probability that, that's actually an upper bound is always in delta, then you sort of crank through the machinery of path learning, and it gives you good bounds. So I'm not going to go into the details of all of this, but this is basically how it works. Right, so Cn here is somehow it's sort of the analog of Occam's razor in science, right? That you pick the simplest hypothesis you can. So this is not quite the same thing because you're not failing it as a hard constraint. But our optimization problem, we are sort of penalizing more complex hypotheses. So that's what's going on. Okay, so that was all sort of one side of the story. So the third story. The fourth story is very similar. But we're going to get rid of all of this stuff with IIT data and all of that, and so we're going to go into the realm of online learning, which superficially looks kind of similar. So in online learning, it's almost the same setting, except your data points, you're not making any assumptions about how they're being generated. You're not assuming that they're drawn from a random distribution. Usually, what we think of worst case settings, so imagine that there's an adversary who's picking these things to make your algorithm perform as badly as possible, right? The difference here is that since it's an online setting, you aren't just given a whole bunch of data points and then asked to produce a hypothesis. Instead, you're given each data point one at a time sequentially, and before you see each data point, you have to produce a hypothesis. So your best guess based on the data that you've seen so far, right? And then you're evaluated based on, so you produce a hypothesis, FP, and the loss that you get is loss of FP given XT, right? And now, if you just wanted to minimize loss, it turns out that that's basically impossible because the adversary could just make an XT that gives you really bad loss on the thing that, because you have to produce a hypothesis before you see the data, right? So maybe the adversary just produces data that makes your loss really bad, which is why we don't really care about loss per se, but what we do care about is this quantity called regret. Right? So in some sense, regret is measuring the fact that if the adversary gives you a really difficult sequence of data points, then it's not your fault if you can't, you can't correctly predict that. But you want to perform well in hindsight. That is, you don't want your loss to be much bigger than the loss of somebody who can see all the data points at the end of the game and then produces the hypothesis. Right? And the reason for choosing regret is interesting. So the motivation that I gave is one reason. But it turns out that with this definition of regret, you can also move back and forth very easily between online and batch algorithms. So you can prove that any online algorithm that minimizes regret can be converted into a batch algorithm that has low generalization error and vice versa. Right? So this notion of regret is actually really powerful. And the other thing is, the reason you want to think about online learning in the first place is that usually online algorithms have good computational properties, right? So they are incremental. So if you have huge amounts of data, you might not be able to run batch algorithms on them, but you might be able to run online algorithms on them. And that's still fine because the online to batch converted theorems will tell you that they perform basically as well as any batch algorithm. Okay. So for simplicity, I'm going to assume that the loss functions are linear. It turns out that if your loss functions are actually convex, this is not a big deal because linear functions lower bound convex functions. So if you have an algorithm that has low loss and low regret under linear functions, it's fine for convex functions as well. And the naive algorithm, right? Maybe I should have made this audience participation, but I'm running out of time. Is what would you produce as the T hypothesis? Well, the naive thing to do is just to take all the data that you have so far, produce a hypothesis that minimizes the loss on those, and say that's my T hypothesis, right? So just go from S equals 1 to T minus 1, minimize the loss there, and you're done, right? But clearly this is a story of regularization, and there's a regularization here, right? The problem with this algorithm is that it can have a regret that grows linearly with time, right? What that means is that the longer you play, after playing n steps, you have a regret that is proportional to n. So your regret per time step is not dropping, and that effectively means you're not learning anything, right? And the reason this can happen is because the adversary can produce a sequence of loss functions that basically make your hypotheses change a lot, right? So for example, if your hypotheses are, here. So if your hypotheses So this is a number line between 0 and 1. And let's say your loss functions are linear functions. So this is your first loss function and this is your second loss function or whatever. If you're just minimizing loss functions on this interval, the minimum will always be either 0 or 1. Right? It's linear functions on the boundary interval. And so you will always be producing something between 0 and either 0 or 1. And the adversary can make it so that you essentially produce 0, 1, 0, 1 and just keep alternating between them. Whereas, a better option would have been maybe pick something in the middle at some point, right? So the adversary can produce huge changes in the location of this minimum just by small changes in that loss function. And you want to stop that. And that's very similar to the reason that we take regularization before, right? You want some sort of stability in the hypothesis that you produce. And so this algorithm is called follow the regularized leader. It's almost the same, except there's you're minimizing, there's a regularization term in this thing you're minimizing. And there's an eta, which is just a constant, just like the learning rate, right? So the bigger eta is, the less R matters. And it turns out that this algorithm does give you good trig rect, so it gives you on the order of square root of n trig rect. If you pick eta appropriately and you pick R appropriately, and when I say appropriately, people know how to pick these. It's not just there exists some eta. There's an equation for what eta you should pick with your trig rect and what R you should pick. And it turns out that the regularizer you should pick here. So I'll come back to that in a second. So so the presence of the regularizer in that optimization prevents the hypotheses from changing too much between terms, right? So, and the choice of the regularizer will depend on the shape of the hypothesis space. So, for example, if you're picking vectors in the unit call, so for example, if you're doing linear classification, you might be picking vectors in the unit call, and usually you use something like gradient distance. If you're picking probability distributions, right? So, for example, you have k actions, and you want to randomly pick an action, so you want to produce a distribution. Then you might use something like entropy, because entropy or negative entropy, because that gives you good trig rect, right? So you want to pick a regularizer that matches the shape of the actions of the algorithms, or predictions, I would say. Okay, so that was kind of yet another story. Remember that in this story, the optimization function looked the same. You are optimizing loss functions plus a regularizer, but the motivation for it was quite different from what we did for the path learning case or for the Bayesian learning case, right? So it's just another story, but it gives you the same outcome. And then this is almost like half a story. I'm calling it an epilogue, gradient descent. And I'm going to go here gradient descent. Okay, so that follow the regularized leader algorithm, it had this form: minimize the loss on all the data you've seen so far, plus a regular number, right? And that could mean keeping around all the data you've seen so far, and that's not good, right? That's not an incremental algorithm. It turns out that algorithm is, in some cases, it's mathematically equivalent to this algorithm. What this is doing is it's minimizing just the last loss function, right? And when I say it's equivalent, I mean that it produces the same outputs as the other algorithm, right? But how does this algorithm remember all the previous loss functions? Well, what this algorithm can do is it can remember the result of solving the optimization problem for all the previous loss functions. And somehow if it could use that memory of all the data it had to produce the next guess, right, then you would effectively be getting the same thing. And it turns out you can't do that if your loss functions are linear and your regularizer is convex, strictly convex, and so on. And it turns out that you want to do something like this. You want to minimize the loss of the last data point, plus this thing called the Bregman divergence. And this Bregman divergence is no longer a function of one argument like the regularizer was, it's a function of two arguments. And you can kind of think of it as a distance between this and this, right? So what this term is saying is that I want f to be close to ft minus 1, or the next f to be close to this one. I'm not going to go into a lot of detail on what the Bregman divergence means. I put all of these in double quotes because it's not really a distance under mathematical definition and so on. Right. But one example could be that if you pick the regularizer to be the square Euclidean norm, so f squared, right. So if you have linear losses and you're picking the regularizer to be the square Euclidean norm, then the Bregman divergence for that regularizer is just the Euclidean distance, right? So that is sort of the touchstone to the standard thing that we know about. And it turns out that in that situation, mirror descent becomes what we think of as a standard gradient descent. Right? So you're getting a sequence of loss functions. You're taking the gradient of the loss function at whatever point, and then you're moving a little bit in the direction of the gradient. Right? So that's what this is. This is the linearized loss function. This is the old hypothesis. Right? Now this is interesting because even though this is a standard gradient descent, we are sort of bringing it up as a special case of this morded with mirror descent algorithm. And it turns out that the mirror descent algorithm has nice properties. It is somehow the only correct algorithm. And this is like a special case of it. But you have to justify why you picked this to be a regular algorithm, right? But once you do that, the gradient descent algorithm falls out. Right. So in a sense, a standard gradient descent, when you do gradient descent, you might think there's no regularization going on there, but implicitly it came out of, like if you look at the mathematics of duality and so on, it came out of the implicit choice of using the square Euclidean norm as a regularizer. And because of that, you should, like if you're just thinking of doing gradient descent on some space, you should be thinking about, does it make sense to use gradient distance in that space? Right? So for example, if the space I was talking about was probability vectors, then using Euclidean distance doesn't actually make a lot of sense, because what is the Euclidean distance between two probability vectors? It's not a very useful quantity. But something else like entropy might make sense. And you can do all of this using entropy, and you get a different algorithm instead of instead of this algorithm, you get a different algorithm. You actually get the exponential weights algorithm. And so, yeah, so that's just something to think about. Yeah, so that's pretty much what I wanted to say, a few stories. So just to wrap up what I was saying, regularization, right? This idea of regularization, it shows up in many different guises, in different fields of machine learning and statistics and so on. We shouldn't get caught up in the different terminology, but we should recognize that there is a unique idea underlying all of these things. And understanding that different communities refer to the same idea by different names might help collaboration, right? So all of these things are basically the same thing. Bayesian priors, complexity regularization, mirror maps. Mirror maps are like their function R, regularization in mirror descent is also called a mirror map. Right? So different communities might prefer to use different ideas, but ultimately it's all the same thing. So, yeah.
Is it possible that they aren't the same idea?
Yeah.
There are just 5 different ideas, or at least 2 or 3 different ideas.
Right. I think that is possible. I mean, like you can get very philosophical about what an idea is. I think that a touchstone is if somebody sits down and they have all of these philosophical things and then they write an algorithm, and then you look at what the algorithm does, that is somehow the essence of the idea, right? And the reason I'm grouping them all together is because when you actually do the math and you write down the equations and you write down the solutions to them, you get similar solutions across all of these things. Obviously, the motivation for these ideas is different, and different communities might go in different directions. But in the end, if they're producing the same algorithm, then I want to think of them as similar ideas.
It's just a quick comment. I think perhaps the details are still matters, even though it's nice to feel it under this general, say, regularization. But for example, I've heard when L1 regularization is really popular. People use L1 regularization in analyzing some images to get some, but then statisticians did theoretical work, and they say it could, because it can also be viewed as a prior. Then they did say that has some shortcomings. When you look at it from the prior view, you see when you get higher resolution images, somehow the L1 regularization would not be helping them more. Like they can see it from when they analyze what is the corresponding prior. That's lately I remember from one talk.
Yeah, so that's actually like a really good example. I don't want this talk to imply that you don't need to think about all of these things separately. This talk should have been full of asterisks with little footnotes because I made all of these hand-wavy assumptions about this is the same as this under certain assumptions and so on. So I don't want to imply that you can kind of get rid of all of these separate fields and collapse them into one thing. But once you do know, sort of, when you're working at a, when you're doing math at a more intuitive level, right, which is where new ideas come from, it helps to know all of the different ways that you can look at things. So like what Jamie said, if you just think of L1 as this function that you stick on your end of your optimization, sure, that's one way of looking at things. But then if you turn around and say, what does it make sense to think of that as a Bayesian prior? And maybe it doesn't make sense, and maybe something else does make sense. So that's kind of the sense in which I want you to take this talk. That by looking at the same thing from different perspectives, you have more sort of filters and you have more ideas that you can apply to the problem.
So I have a question about if there are any rules of thumb for choosing a regularizer in the mirror descent case. You said what sort of makes sense for the data. Is there any way to like learn that from the data?
So it actually doesn't depend on the data. It only depends on, because in online learning you try to avoid making assumptions on how the data is generated,
right.
But it does depend on the shape of your hypothesis space. So for example, if your hypotheses are probability distributions over things, right. Then the entropy regularizer usually makes sense, etc. So it's and it turns out the simple rule of thumb is you want to pick a okay. So maybe I'll give a little demonstration of what happens when you pick the wrong regularizer for a particular problem. So let's say that you're working on a probability syntax, right? So you're working on probability distributions over two things. Vector, so essentially it's this space, right? It's a space of all vectors that add up to one and their probability. So your algorithm is picking probability distributions, right? So now it turns out that the quantity that shows up in the regret bound is basically the maximum value that the regularizer takes on this space, right? Now if you, in 2 dimensions, the size of this space is basically the square root of 2, right? And in d dimensions, sort of the diameter of the probability simplex when measured at a Euclidean distance is something like the square root of d, right? So you will get something like square root of d regret if you pick, the Euclidean distance regularizer if you're working on probability distributions. But instead, if you pick the entropy regularizer, the maximum entropy distribution over d things is a uniform distribution, and the entropy of that is something like the log of it, or the negative entropy is something like the log of it, right? So if you were to pick the entropy regularizer for that, then you would get something like log of linear, which is not the square root of linear. So that's like the very sort of symbolic, mathy way of saying it. But intuitively, it also makes more sense that when you're comparing two probability distributions, you care more about entropy. And it turns out that the corresponding segment divergence is scale divergence or cross entropy. So, so in some sense, it's nicer, but it's also supported by theory. The reason I wanted to give these different stories is to say that the different stories are going to give you different rules of thumb on how to pick a good regularizer. So if you're coming from the pack learning world, right, you will have a different set of theorems that tell you how to pick good regularizers. And if you're doing Bayesian analysis, you will have a different people or whatever, right? So for online learning, you will have different. So the different facets here are just giving you different rules of thumb, but it's ultimately the same thing. And sometimes it might make sense. For example, fast learning analysis can be sometimes very hard, and so it's much easier to pick regularizers in online learning setting. So if you have a problem, it might be easy to pick a regularizer that would work in online learning and then see what it does for fast learning, right? Because it's similar, right? Even if you can't directly do the theory. Questions?